Alright, week 13, Control 3020, 26 Winter, Fanshawe College, London, Ontario. It is a review week, so we already established that we're probably going to eliminate quiz 4 because maybe there's no need for that. Although if somebody wants some additional exercises, just come over, join me in the lab and talk on the side or something like that. I'm fine with this. There's one or two people that approached me about that test, so just come over during any of those lab sessions. Just make sure if you're planning to attend any of the lab sessions, which is this, we're still continuing with the lab test. So if you have done it already this week, you do not have to come for the labs. Okay. Next week we're just going to have one last lab. Unless you have some open lab to do as well, you can do that this week as well. But throughout the course, you were able to do this all the time, so I probably got used to the routine, so that's fine. All right, so that we take care of that. Test. The final test is going to be, Monday for the first group and Wednesday for the second group of next week. This way, you can get this thing out of the way. Concentrate on other subjects. Also, what's going to be on the test? It's going to be pretty much a combination of those two tests, test 1 and test 2. All right. Until I administer that test or two for somebody who had bet off a hurdle, and it was an honest thing, so then I will be able to. But just come over this week, and so I can just post those questions, so you can see similar questions that were on test 1 and similar questions that were on test 2. There won't be any of the same questions. Right? That's why I was able to give the test back to you. Right? So that. As far as that, we can, All right, so these two lectures today are the review. So I'm going to have review part 1 now and review part 2 after this. You don't even have to participate in this. Well, you don't have to participate in anything, but it's a good idea. So we're just basically reviewing this whole thing. You can also, I encourage you to go through the notes, go through the YouTube videos that we have posted, and just familiarize yourself with some of the just refresh some of those aspects of whatever we have done. All right. Okay. So let's get it on with this. Are we recording? Yes, we are. Okay. I'm always paranoid with this. Okay. So let's just review this Pascal's law that we were nurturing throughout the last 14 weeks. All right. Okay. In this context, hydraulic and pneumatic power transmission system in the context of Pascal's law, in the context of hydraulic and pneumatic power transmission systems. The objective of this blah 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 lecture to bridge the conceptual gap between the fundamental physics and practical engineering, to explore how the pressure behaves within confined fluids, and how we exploit the behavior to move massive loads in hydraulics to perform fast operational tasks, pneumatics, and right away we can just say that, okay, so we have hydraulics associated with power and pneumatics associated with speed, okay, but at the cost of power, and with hydraulics we have the power at the cost of speed. All right, cool. All right, let's go. Fluids. Definition of fluid is any substance, liquid, gas, plasma, or other material that continuously deforms or flows when subjected to a shear stress, otherwise sideways force, and has no fixed shape. It just takes the shape of the container. Adapting to, okay, all right. Unlike solids, fluids, which means liquids and gases, have very weak bonds between the particles, which means that they can flow freely and cannot hold their shape against constant sideways pushes. Key characteristics: fluids flow easily, particles can move freely past one another, allowing the substance to float. Try to play this back at twice the speed. All right. Fluids have no fixed shape. A fluid takes the shape of the container. Fluids yield to shear stress. It continuously deforms under sideways force, whereas a solid would resist and spring back. States included within the fluids: liquids, gases, and even plasma, like in stars or fusion reactors. Are considered fluids. So liquids are considered fluids. Liquids and gases and even plasma. So they're fluids, all right? Because they exhibit these properties. Fluids examples, these properties that we just mentioned here. Examples: liquid, water, oil, honey, all right? Air stream. I don't remember having a honey cylinder, honey operated cylinder. That would be actually, okay. Cool. So gases: air, steam, helium, plasma ionized gas. That would be, what was I going to say? Fluids. As far as pneumatics, they are compressible because gases are compressible and liquids are incompressible. All right, fluid power definition. What's the fluid power? It's the use of fluids, liquids or gases to transmit power from one location to another. Hydraulics using relatively incompressible. Always says relatively because it compresses just a little tiny bit, right? But for our purpose, we ignore that compressibility for what we're studying here. So using relatively incompressible liquids, oil or water. Pneumatics using compressible gases, usually air. Both systems rely on Pascal's law. All right, so what do we have here? We have a cylinder, we have the chamber, and we have the pressure inside that container or the chamber between the back wall and the other wall of the piston here. We have a shaft. So the pressure acts on the area and it creates force. Cool. All right. Pascal's law. Pressure applied to a confined fluid. So we're talking about the static type of situations instead of dynamic or kinesthetic. All right. Because we are not dealing with the fluids that flow. We're just having the fluids that do not flow. They're just trapped in a closed system. And we're acting on it with what? With pressure. We can move fluid from one place to another, but we are not studying the flow of the fluids here. So pressure applied to a confined fluid is transmitted undiminishedly in every direction throughout the fluid and acts within the equal force in equal areas. So the pressure at any point in the contained fluid is the same. At any point we have equal pressure. And the pressure acts on the walls. How does it act on the wall? At the right angle to the tangent of whatever the area would be. So pressure exerted on a confined fluid at rest. All right, fluid at rest. We're not dealing with the flow of the fluids. We're talking about acting with pressure. So the pressure exerted on a confined fluid at rest is transmitted in undiminished all directions and acts at the right angles to the containing surfaces. So there are two perspectives here on Pascal's law. Here is the formula: pressure equals force over area. Pressure equals force over area. What units? Oh, that's a good question here. As I said, well, I'm glad you asked that question. Okay, it's an excellent question. I'm glad you asked it. All right, so pressure. What units are we using? Okay, so Pressure, force, and areas. Okay, so we have two types of measuring systems or metering systems. US, it used to be called imperial, but England switched to metric system a long time ago. In some cases you're going to see US customary unit, so that would be the same as imperial, right? So pounds, not kilograms, and things like that. Force, we're talking about usually in the imperial system would be the pounds, and newtons in the SI unit, metric. Area, we're talking about square inches and or square meters in the metric unit. Pressure, now here's where the fun begins. So in imperial we're talking about pounds per square inch, right here, pounds per square inch, or we can just call it PSI, pounds per square inch. In metric system we got newtons per square meter. 1 newton per square meter is equal to 1 Pascal. Okay, go back to the imperial. We have bars, and we also have bars in the metric system. 1 bar is equal to 14.7 pounds per square inch, or 1 bar in metric system is equal to 100 kilopascals. That's it, 100 kilopascals is 1 bar. 1 bar is 1 atmosphere. 1 bar is 1 atmosphere. So we are sitting in approximately 1 bar, sometimes slightly higher, sometimes slightly lower. If the pressure is slightly higher, like 102 kilopascals, then we feel great, we feel energetic, and we feel happy. And when the pressure goes a little bit lower, maybe 98 kilopascals, so less than 100 kilopascals, then we feel sleepy, and we just want to stay home and sleep, right? 1 atmosphere pressure at sea level equals to 1 atmosphere, and it's equal to approximately 1 bar, and it's equal to 100 kilopascals. How do I remember the 100 kilopascals, 1 bar, 1 atmosphere? Is whenever you see the weather report, sometimes quite often they just give what the pressure is right now, and what is the pressure going to rise, or is the pressure going to come down. So there's low front or high front, what they say, and there's going to be 1 and 2 kilopascals moving in. That means it's going to be nice weather. And when the pressure is low, less than 100 kilopascals, then you're going to have some rain, cloudy, and things like that. So I remember that 100 kilopascals, 102, 98, or something like that, right? So that's the units for the pressure. I encourage you to kind of look at this thing once in a while. And yes, you're going to have the formula sheet from the last test, and you're going to have the formula sheet from this test to deal with, to write the test. If you, wish to write the test in the test center, it's time to contact them now, right? But last time nobody chose to do that, so that's fine with me as well. Happy to have you in class. All right. Mechanical advantage. All right. Pressure equals force over area. All right. Since the pressure is equal everywhere, so pressure 1 equals pressure 2 if we have 2 different cylinders and with different areas. So pressure is equal everywhere. So pressure over the area in one cylinder has to be equal to force 2, and area 2 when we're talking about the force that we're moving here, the shaft. All right. So we have the mechanical advantage. If the output piston A2 area is 10 times larger than the input piston area 1, then the output force, F2, will be 10 times greater. Awesome. At what cost? At the cost of the distance, right, that the cylinder is going to move. But you can just do more strokes and lift a car with one hand. Whoa, look at me. All right. Now we're talking about work. Definition of work. Work is energy transferred to or from an object when a force causes it to move or displace, if you want to be technically smart, in the direction of the force. Work is energy transferred to or from an object when the force causes it to move, the object, in the direction of the force. Work is calculated as force times distance. Work equals force. This is not an and, this is times. Distance times the cosine of the theta if the object moves under an angle, in a different angle, at a different angle that the force is applied. The example would be if you have a train car on the tracks, it is going to move up and down the railroad tracks. Whether you push it directly in the direction of the tracks or you would push it at a slight angle, it is still going to move on the tracks because it's not nowhere else to go. So that would be, then we would consider the angle. But since we are dealing with cylinders here, we don't consider the angles because all the force is happening here in the cylinder. So the force is applied or exerted within the direction of that. So this is just like the railroad tracks here. The cylinder can move either way. So if you have a hose here and there's another cylinder that you act on in order for this one to move, we still do not consider any angle because the force is directly in the direction of the movement and the in one cylinder and in the other. Doesn't matter how those cylinders are arranged within each other. So here's the mechanical. Okay, the mechanical work. All right. When acting upon a cylinder, we are pushing directly along the path of the piston moves, which is basically the displacement is technically zero. The force displacement, even if two cylinders are positioned differently in space, cosine of 0 degrees equals 1. So whatever times 1, we just can skip the 1. Therefore, the cylinders, you only need to simplify the formula. And in our case, work equals force times distance. Units of measurement is the metric system, or the standard SI unit is joule. Right. 1 joule equals work done when 1 Newton moves an object 1 meter, the distance of 1 meter in the direction of the force, but we already talked about that. 1 joule equals 1 Newton meter. 1 joule equals 1 Newton meter. If you want to talk about the imperial system or US customer for units or system, foot-pound. How many foot-pounds? Foot per pound, or foot-pounds, not per pound. Foot times pound. Common unit is in the English system. Okay, 1 joule equals 0.737 foot-pounds. 1 foot-pound equals 1 point. Okay, so here's a bit of a conversion, and you're going to have that as well. All right, conservation of energy, the trade-off. We get multiplied force, but we don't get free energy. Okay, so the distance versus force. To move a heavy load a short distance to the smaller input piston must travel much further. The smaller piston must travel much further with the distance 2. So work. In order to move things, to lift a car with the car jack. All right, force times distance. 1 in one cylinder, force times distance in another cylinder, because work in equals work out. We don't gain energy, we don't lose energy. Well, sometimes we do lose energy if things turn into heat. Okay, that's where our energy laws are. So you see here, if you increase one, so increase that, you have to decrease the other one in order for the equal sign to be there. Same as the transformers. Power is being kept. Voltage times current on one side, on the primary, has to equal to voltage times current on the other side in a transformer. So if you raise the voltage on the other side, you have to decrease the current. That's how high voltage lines became to be. Conservation of volume. We don't, within the closed system, we just have to work with one type of volume, both cylinders. So volume displacement, volume lost in the input cylinder equals volume gained in the output cylinder. They are connected to each other. System is closed, so nothing gained, nothing lost here. So volume equals area times distance. Area times distance. Volume. All right. If we have a square container, this would have an area. How tall is the square container? How tall is the square container? So here's the area, and here's the distance. All right. Cool, eh? And that gives us the volume. Because the volume has to be conserved. It doesn't leave. It gets displaced from one cylinder to the other, but if those cylinders are closed within a closed system, then we are not spilling the volume anywhere else. Or we're not gaining any liquid, more fluid. So volume of the liquid displaced, volume liquid that passes a point in a given system during the specific operation. Okay, so here's the definition. Area 1, area 2, distance 1, distance 2, area of the first at the first point, area at the second point. Or just the picture that I just drove. And we have two different cylinders. Here's a cylinder. Here's another cylinder. And they're connected with a hose. So it's a closed system. Here's a piston. Here's a piston here. You push that this much distance, this far, you have a little bit of volume that you displaced. Or that volume is going to go there. Or let's say you moved it this much, this far. Okay? You moved that cylinder going right to this point. So you have displaced that much volume. So the area of that base times the distance that so you get the volume. It has to be equal to the same volume, so you're not going to cover the same distance, you're going to cover less because you have a bigger area, so the volume kind of distributes there. So you apply, the force is multiplied. If the area is 5 times bigger than that one, you get 5 times more force, but you get less distance. Assuming that the fluid cannot be compressed. Okay, yeah. So with oil, with liquids, it works bang on. With air, where air is compressible, you get to account the compressibility of the fluid, which will be the gas, air. The volume of the fluid pushed through a wider section must be equal to the volume of the fluid, so which is basically what I just explained here. All right, let's keep going. A little bit of problem to solve, hydraulic service lift. All right, so as a reminder, how does this work? Here's a check valve and here's a check valve. Here's a reservoir tank. And, well, we're displacing volume. So here's the smaller cylinder right here. There's a bigger cylinder right there. And here's the heavy, heavy load, and here's your little tiny hand. All right, so you're just pumping that. How is it that you're able to do cover long distance? Well, you just keep adding the strokes, keep adding the distance with every stroke that you do. And how is that the check valves work? When you push that cylinder here, see that check valve is going to close, so I'm not allowing the fluid go back to the reservoir tank, but this check valve is going to open, so the fluid is going to go in there with whatever volume here. And then when you stop applying pressure, that pressure is going to close this check valve, so that's going to close, so it's going to be kept here. So we lifted it and, well, it's lifted. Now you stroke again, but on the backstroke here, you're creating a vacuum at this point, so that opens this check valve, and that sucks it in here. So this one closes, this one opens. We can get more. We can just get more volume here, more liquid. And then you push it down again, so this check valve is closed, this one opens, we get more, right? So we just keep pumping, and little by little by little we can get this load high enough that we want, right? And then if you just open up the release valve, then the whole pressure equalizes, goes back to the reservoir tank, and that's because there is a pressure downwards here. That is going to come down, and this oil has to go somewhere, so through this pipe right here is just going to flow back to the reservoir tank. All right. So what do you have? A car mechanic uses hydraulic lift to raise a vehicle. The lift contains a small input piston and a large output piston connected okay, so here's a small, here's a large. The input piston has a cross-sectional area of 5 squared centimeters, or centimeters squared. That would be the area 1. The output piston, which supports the car, has the cross-sectional area larger. It's 100 centimeters squared, or 100 squared centimeters, and we consider that as area 2. Question: if the mechanic pushes the input piston down 20 centimeters, which would be the distance 1, how many centimeters was this thing going to go? So here is the formula here. Volume has to be equal to volume 1, volume 2. Okay. So area 1, distance 1 equals area 2, distance 2. So we know the area 1, we know the area 2, we know the distance, we just don't know that distance here. Right? Mechanic pushes down. How many centimeters will be lifted? Yeah, okay, so we just don't know that one. We could derive D2 from all this formula here. So what do we have to do? We just have to divide everything by distance 2, by D2. So divide this by D2, we got area 2. No, we just want to divide everything by A2, because that's what we want. So we're going to have D2 equals area 1 times distance 1 divided by, because we have to divide both sides by the same thing in order to keep the equal sign, and we get 100 centimeters cubed of the volume divided by 100 centimeters squared. So we still get to keep the unit, because we cancel that. If this was 2 and this was 2, this would be unitless, but no, we need to have some centimeters because of distance. Right? So good, it checks out. Cubed 3 minus 2, it's going to give us just 1 to the power of 1. So we just don't write that. So yeah, the units check out. Good. So 1 centimeter. You can always do the ratios here. 100 to 5. 100 divided by 5. All right. That's going to give you the ratio. So it's going to give you 20. Right? 20 to 1. Oh, look. 20 to 1. Right? All right. You can do this much faster here, right? Because just knowing the areas. Right, hydraulics versus pneumatics. We talked about that. Compressibility, pressure levels, precision components, hydraulic liquid or pneumatic gas. Hydraulics, incompressible, immediate response. Pneumatics, it's compressible. Pneumatics gases are compressible, so you get spongy, delayed. You can talk about something like a proximity delay. If you're really stubborn, we could say that. Pressure levels very high in hydraulics, up to 10,000 psi, and lower, usually 80 to 100. Okay, 150, so much less. Remember when we were dealing with the regular pressure in our trainers, we would get something as 2 or 3 bars when we were dealing with the pressure that we were using in the pneumatics labs. But we also have, we dealt with the hydraulics, and we dealt with 20, 30 bars. So already big difference in the trainers there. Precision, hydraulics have high precision and smooth action. Pneumatics, good and fast, repetitive tasks, but you don't get that precision. If you want precision, go hydraulics. If you want power, go hydraulics. If you want to speed things fast, sometimes you want that. Components need reservoir tank and return lines for the hydraulics, and components vents used air to the atmosphere. Alright, vents use, okay. We use the vents to spit the air back into the atmosphere. Alright, it's for the pneumatics. Alright, real world applications, hydraulics, heavy machinery, wherever power is needed. Automotive braking systems, yes, we use that. Aircraft landing gear and flight surfaces use hydraulics. Pneumatics systems, factory automation, pick and place robots a lot, jackhammers and air tools, bus doors and truck air brakes. Right? Summary and conclusion. Pascal's law is the heart of flowing power. By manipulating the force area, we can multiply the force. Yeah, multiplying or manipulating the force area, we can multiply the force to perform tasks impossible for human alone. Yeah, the carjack is the best example. Hydraulics excel at massive force and precision. Pneumatics excel at speed and simplicity. All right. We had some problems here. Do we have time? Yes, we do. Let's just do one. Hydraulic jacks. Okay, we did that. Distance and displacement. Using the same jack. Okay, problem 3. Pneumatics. An industrial pneumatic press needs to exert force of 4,000 newtons to stamp a metal part. The factory airline provides a constant pressure of 500,000 pascals, or it would be 5 bars. What is the minimum surface area required? Alright. Do I have the solution here? Yes, we do. So I don't have to strain. So the problem 3. Do we have the problem 3 here? No, we don't. How can we tackle this one here? We have the pressure; it's constant. We have the area. What's the minimum surface area? All right. First in the metal part, the factory provides pressure of 5,000 Pascal bar. What is the minimum surface area? Well, this is where we look for that. Pressure is equal to the same. We apply this formula here. We got the force 2, area 1, calculate area 2, derive area, so multiply everything by area 2. So we're going to have F2, or no, sorry, divided by F2, so we have area 2. And so if you divide that, so it's going to be F1 over A1 times F2 here. And that's how we would find the minimum area. Right? The piston is circular. What? Okay. Yeah. So that would be the formula that we would use. Practice problems. Problems of distance replacement. Go over those. I'm not going. We've done it already here. So apply those formulas. Just go over those ones, understand them, refresh those things for yourselves. Okay. Another last slide. All right. Oh, here's the problem 3 here. Right. So force, pressure, area. There you go. Right? That's the one that we would use. And yeah, we can go over that. We could go over that. I'm not going to go line by line, just reading it. So we have those notes. They're posted. Go over those. All right. I might ask you some questions about that stuff. All right. Another one here. Let's go. All right. We talked about astable, monostable, and bistable multivibrators. So we're just going to refresh that in case somebody missed. So multivibrators, triggering, or multivibrators, synchronous, asynchronous devices. All right. Multivibrator is an electric circuit. In our case, we can apply that to a hydraulic or pneumatic. So that would be the oscillator that we would do. It would be a multivibrator. Or we could have a monostable, bistable, or astable. Right? So we can compare that to the electronic devices. The multivibrator, it's a device such an oscillator, timer, latch, or flip-flop. I'm not sure if you studied flip-flops yet. Implements a variety of simple two-state systems, such as high or low in electronics, or we can compare that to our cylinders, extended or retracted. Or extended, retracted, extended, retracting. Extended, so that would be an oscillator. Right? Produces an output when triggered. Multivibrator types: astable, monostable, bistable. Astable multivibrator continually switches from one state to another. Internally triggered and does not have any stable state. Example, an oscillator. It will be an astable multivibrator. When we did during our labs, the cylinder that just goes back and forth, back and forth, back and forth, that doesn't stop, that would be an astable multivibrator because it doesn't have any stable state. A stable, monostable, for example, also known as a half astable multivibrator, half. One of the state is stable. The other state is unstable or transient. Which is basically means like momentary. It idles in one state, which means it has a resting state. So the cylinder would have a resting state extended, or will have a rested state retracted. We're translating this electronics devices into the hydraulics here, or pneumatics. The other state is triggered momentarily into its transient state. Okay, a trigger pulse causes the circuit to enter the unstable state. After entering the unstable state, the circuit will return to the stable state after a set time. Examples: a momentary push button switch, a pulse detector, or a cylinder that we just did. When triggered, it extends. Well, as soon as you release the trigger, it comes back to its resting state or the stable state. So there will be a monostable multivibrator. It will be single-acting cylinder. That would be an example of that. It has a spring that pushes it back into the resting state. You pressurize the cylinder, it changes its state into the momentary or transient state. Really release the trigger and it comes back on its own and it stays there when we don't act on it. So that's a monostable multivibrator. It does have one stable state. A bistable multivibrator has two stable states. It can be stable in either state. It can be flipped from one state to another by external trigger or pulse. Example of flip-flop. Not sure if you have studied those yet, but double-acting cylinder, that would be it. You apply pressure to the one port of it, makes it extend, and then the pressure collapses. It stays there. So this has have a stable state and extended until you apply pressure to the other port, and you're going to retract it. The pressure disappears, and it's going to stay there. So it has two stable states. Triggering, level triggering. I left that on so you could satisfy your curiosity what I mean by triggering here, but this is not electronics course here. So you're welcome to use that in other subjects there. All right? How much time do we have? We have time to select one more because this is going to be recorded part 1. So whoever comes to the second part can watch this recording. Whoever comes to this part, you can stay and log into the other link and just come back and continue, or you can watch the recorded video later. Okay. Can we start another one here? Yeah, we can start. Let me just cue things up. Got the Pascal's law of week 1, week 2. There was a supplement that I just gave you. Let's go week 3 here. Oh, yeah, okay, we got the reactants. Yeah, we can quickly go over that. Frequency-independent components. All right, let's see what we have here. Reactants and impedance. All right, background reactants. So we have the resistor, capacitor, and inductor. Inductor, it will be a coil. Resistor is a non-reactive component because, well, the current and the voltage are always in phase. It doesn't react to the frequency changes. A 100 ohm resistor, pure resistor, is a 100 ohm resistor, whether it's a DC current you're passing through it, or whether it's AC current you're passing through it, whether you increase the frequency or decrease it, it's always 100 ohms. Capacitor is a reactive component because its quote-unquote resistance value changes if the applied frequency changes. Capacitors love change. Inductors do not like change. They oppose change. So when you apply, all of a sudden you start pushing current through the capacitor, it is going to start conducting right away. So you get the current first across the capacitor. When the capacitor charges, the voltage is going to build on it, but the current is going to stop. So to a DC, when there is no change, capacitors do not like that, no change. They always like the change. They can't sit in one place. Coils or inductors, on the other hand, they do not like change. They want things to stay constant. They're the opposite of capacitors. So, when you apply, all of a sudden you apply from 0 volts or 0 amps, try to push a lot of amps or some amount of amps of current through a coil. At the moment of change, the inductor is going to give you a hard time. So we get 0 current, but we get the voltage across the coil. So first we got current in a capacitor and then the voltage, and we got the opposite. We got voltage first and then the current is going to start building up. Because the resistance of a non-linear, I was going to change that, non-reactive components, because, or the reactive, sorry, because, okay. I got it. Because of the resistance of the reactive components, because of the resistance of the reactive components is affected by the frequency changes, we can say that the capacitor has a reactive resistance. We call it a reactance. The resistance is different. Its resistance is different depending on the frequency. So since capacitors like change, the more change the better. The higher frequency, the capacitor is going to resist less. And inductor is the opposite. So in capacitors, the capacitive reactance, we label this thing as XC. And here is the formula here. XC, the capacitive reactance, is 1 over 2 pi Fc. 2 pi, we know what that is. F stands for frequency. C stands for capacitive in farads. Capital F. And it also stands for frequency. Right? So inductors, inductive reactance, XL, is XL equals 2 pi FL, not 1 over. Right? Which makes sense. You increase that frequency in the capacitor right here. You increase that, the whole number is going to get smaller, which means the capacitance is going to get smaller. So more frequency, faster changes, higher frequency, capacitor is going to resist less. In inductor, frequency increases, that number is going to increase. So makes sense. They do not like change. Not that here. All right. What is impedance? All right. Here we have a circuit with a resistor and capacitor. Here is the power supply voltage. So it's, I put a square so the change is sudden. So suddenly the power supply changes. Not a gradually, not a sine wave, it's a square wave here. And this is a capacitor. So here's the current. Capacitor starts charging with inrush current. Bam! The current flows. If the current flows to the maximum, it just basically acts as a straight wire, so the resistance across that is 0, which means you get zero voltage across the capacitor. But when the capacitor charges, it's going to take current at less rate. It's going to just, yeah, okay, I'm satisfied. I'm just not thirsty anymore. So I drink less. I'll drink less. Okay, I can't drink anymore. I am full. Stops conducting, stops the intake of the electrons, and when the current stops, that means the resistance is great. The greater the resistance, the greater voltage across it. Until the thing changes the other way, and the other thing happens all over again. If you have that kind of a type of wave in the now at the power supply. If you have gradual, it's going to look slightly different. That is going to, but I just wanted to have the drastic changes here. Coil on the other side. Here's the inductor. Power supply changes. Bam! All of a sudden it changes. It does not like the change, so it's going to oppose. It's going to stop the current flow, which means it's going to have a lot of voltage. All the voltage is going to be across that. But then if you don't change, the coil says, okay, if you don't change, I'm going to start cooperating, and it starts conducting the current. Until it starts conducting current, it conducts the current to the maximum, which means that it's going to act almost like a straight wire with zero resistance. So if you have a zero resistance across this component here, then the voltage is going to drop. Opposite of capacitor. Here you have side by each, or side down underneath each. Okay. Might as well cover this part. In a circuit. Now, whether this conductor, the inductor and the capacitor are connected in series, or we have the so if we have capacitor and inductor connected in series, and we try to push current through that, or we have capacitor and inductor connected in parallel. We apply voltage here. We apply voltage here. Alright. Now, if we apply the sine wave here, then fun begins. At certain point, let's say we have a capacitor that is 100 microfarads, and we have a inductor that is the value of that has a value of 100. The inductance is 100 millihenries, because inductance is measured in henries, just like a Henry bar. When you have the coil, which is the red line here, and this is the frequency, low, high. This is impedance, so you can just call it reactance as well. This should be reactance. You keep increasing the frequency, and remember, coil does not like change. The more frequency it's exposed to, the harder it's going to resist. So from low frequency, it resists a little bit, but not much. You increase the frequency, the resistance or the reactance is higher. Keep increasing the frequency, it's going to react and resist more, resist more, resist more. As the frequency increases, the resistance or reactance increases. Capacitor is just the opposite. At the low frequency, it resists a lot. Now, because it likes changes, when you start increasing the frequency of the voltage that applies, it's going to conduct more by resisting less, resisting less, resisting less. And if you have two different, if you have a capacitor and a coil, at some point they're going to have the same reactance. And in this case, with 100 microfarads and 100 millihenries, the reactances are equal at 50.4 hertz. It just so happens with these two. Now, let's say, and I'm just picking it out of thin air, the directions. They have different directions. Let's say XC resists this way and XL resists that way. You get put with the same force or the same value, then they're going to cancel, and it's just like having a straight wire. It's just like having a straight wire. Now, when we have on the other side, over here, see that? Over here. This one reacts here, that way, that one reacts the other way. That frequency is going to oscillate between here and here, in this direction and in that direction, and this direction and that direction, that resonant frequency, which means it's almost like a open switch. So current is not going to flow from here to here and through here, because all the current, all the energy is going to get trapped oscillating, oscillating. Okay. Somebody picked it up. Thank you. All right. So if those connected in parallel, you're going to have break in the current because we have built something that's called a tank circuit at that resonating frequency. There is no current flow between here and here because all the current is trapped oscillating back and forth, back and forth. Over here in series, they cancel each other, and one resists one way, the other one resists the other way. They're going to pass through. All right. And that's how this thing would manifest in the voltage. So it's two, those two components are in series. And because the reactances point the other way, opposite to each other, which means that the voltages are also going to point away from each other. And they're going to cancel. So it's just like a straight wire here at the resonant frequency. If you change the frequency, deviate from the resonant frequency, one of them is going to become higher and one of them is going to become lower. You're going to have some overall reactance happening here, which is going to add in series to the resistance. At resonance frequency in series, this is just a wire, zero resistance, and all you have is the power supply, switch, resistor connected to the ground or connected to the other side of the power supply. All right, let me just stop here, and you can switch over and log into the other link. However, you're going to have to wait a little bit for the recording to settle in, so to process. So when you log in there to the other link, please tell the other people who are already waiting there that we're going to have to wait a couple minutes, maybe 5 minutes or 4 minutes, for the process to stop, for the recording processing. Yeah. All right. So I'll see you on the other link.